So we are given this second order system and we are asked to find this 4-time response matrix of the system for a unit step input. So the first thing is to compare the given system with the general second order system representation, which is k omega n squared divided by s squared plus 2 zeta omega ns plus omega n squared. So comparing the two, we can see that our omega n squared is just 25. That means our natural frequency omega n will just be square root of 25, which is 5 rad per second. So comparing the two numerators, we'll be able to know our steady state value or steady state gain. So it will just be k omega n squared is just 10. So it means our k will just be 10 over 25, which is just 0.4. So you can actually find it in an alternative way by using the steady state gain, that is substituting s as 0. So g of 0, which is the steady state gain, will just be 10. And if we replace s with 0, we'll end up with 25 here, and we'll get the same thing, which is 0.4. So now, if we compare the second term, that is the coefficient of s, I will just have 2 zeta omega n is just 6. So I already know my omega. So I have 2 times 5 zeta is 6. So it means my zeta will just be 6 over 10, which is 0.6. So now, since my zeta falls between 0 and 1, I know it is an underdamped system. So subsequently, all the formulas that I will use are standard approximate for the response of an underdamped second order system to a unit step input. So for such system, the damped natural frequency given by the formula 1 minus zeta squared. So I will just have pi 1 minus 0.6 squared, and that will give me 4 rad per second. So this is my damped natural frequency. So starting with my peak time, it is given by Tp pi over omega d, which is just 3.14 all over 4, which is 0.785 seconds. My maximum overshoot in percentage is given by exponential minus zeta pi over omega d times 100%, which is just exponential. I know that my zeta is 0.6 pi all over my omega d is 4 times 100%. So if you sub that, you'll have 9.5% as the maximum overshoot. So this is the second axis. So my rise time is given by the formula pi minus beta all over omega d, where beta is just tan inverse of omega d over zeta omega n. So it's just tan inverse of 4 all over 0.6 times 5, and it is a rad. So if you solve this, you will have 0.93 rad. So if you substitute it here, we'll just have pi minus 0.93 all over 4, and that will give us 0.55 seconds. Finally, our settling time is just approximated as 4 over zeta omega n, which is just 4 over 0.6 times 5. Therefore, the settling time is just 4 over 3, and that is 1.33 seconds. So now let us go to MATLAB and see if we can get similar results from the step response of the given system. So here we are in MATLAB, and I have already defined my system using the TF function, as you can see, and I have my step function here in order to visualize the step response of the system. So I will just click on run. So this is the step response of the system. I just need to put my cursor on the response, and then starting with the peak time. So the peak time is just the time taken to reach the maximum peak of the response. This is the peak value. You can see the amplitude or the maximum value is 0.438. So we'll use this in computing our maximum overshoot. And this is our peak time, which is 0.785. So let us go back to our whiteboard. So we have seen from the MATLAB response that our peak time is 0.785 seconds. So using the data from our response, let us compute the maximum overshoot. So it is just the peak value minus the steady state value all over the steady state value times 100%. So we have seen that the peak value is 0.438. Then our steady state value from the response is 0.4. Then divided by 0.4 times 100%. So if you sub that, you'll end up with 9.5%. So just a proof that the steady state value is 0.4, you can see this dot line is showing you the steady state value, which is 0.4. So the rise time is the time taken to move from 0% to 100% of the final value, which is 0.4. So the time it takes, it started from 0 up to the first time we reach 0.4. So you can see this is the first time we reach 0.4, and we have 0.554 seconds. So our rest time is just 0.554 seconds from the response. So let us look at our settling time. So the settling time is the time taken to reach and stay within 2% of the final value. So if we drag, so the time we reach the final value and then stay within 2% of the final value is our settling time. So you see, this is the time we reach 0.4, and then from here we stay within 2% of the final value, which is 0.4, and the time is 1.33 seconds. So our settling time from the response is 1.33 seconds. So if you compare all the values from MATLAB with the values we obtain using the standard approximate formulas for the unit step response of an underdamped system, you can see that they are the same. So for more comprehensive tutorials on control systems with MATLAB implementation, watch the playlist on the screen. Please like and subscribe to the channel. Thank you for watching.